Hi guys, and welcome back to Hetero Learning. Last video, we took a temporary pause from indice laws to help you guys with working with quadratics in a Crit B test. But today, we're coming back for a second of two lessons on exponents. We will start with the problem shown on the screen. It gives us an equation that has three letters, n, x, and y. It asks us to express n in terms of x and y. Right away, the first thing you want to do for any problem relating to exponents is you'd want to see if you might be able to get as many terms as possible onto the same base. This helps in the same way as combining like terms in a normal mathematical expression. For me, I quickly noticed that on the left-hand side, there is root 3, which I'm thinking should be in some way related to 3. And with the denominator on the right, 27, I believe is 3 cubed. Well, we've just identified that all our exponents can be transformed into ones with bases of 3, so let's do that. Well, something we know about numbers with root signs on them is that, see, here's another indice law, we know can be written as an exponent with the base of that number and with a power that bears the value of 1 divided by the index of the root. So in this case, we have the square root of 3, so that would be represented as 3 to the half power. There are brackets outside this. 3 to the half power to the nth power. Well, that should be, here's another indice law, 3 to the half of nth power. We know this because when the power of a number is brought up to another power, we call this the power of power law. The two powers can be multiplied together to form a new power. In summary, now, we know that the left side of this equation can be written as 3 to the half of nth power. Moving to the right side. Well, same rule here. 27 is 3 cubed. In other words, 3 to the power of 3. That to the power of y should give us 3 to the power of 3 times y, therefore 3 to the power of 3y. We don't need to do much to the numerator because it already has a base of 3, and its power is already in simplest form. But what we can do is get rid of the fraction by dividing the top by the bottom. 3 to the x power divided by 3 to the 3y power should give us, as we've talked about in the first video on indices, 3 to the x minus 3y power. Altogether, we can now rewrite the entire equation to be that 3 to the half of nth power is equal to 3 to the x minus 3y power. Well, that means that half of n must be equal to x minus 3y. It asks us to express n in terms of x and y. So all we need to do now is multiply both sides by 2, so half of n times 2 is n, and x minus 3y times 2 is 2x minus 6y. So that would be our final answer. N is equal to 2x minus 6y. Our next problem is much harder and could be considered a Math Olympiad problem. So it asks us which is larger, 100 to the 300th power or 300 factorial. First, we must understand what the two numbers are. 100 to the 300th power is just 300 of 100s multiplied together, while 300 factorial is 300 multiplied by all the natural numbers below it. So it would equal 300 times 299 times 298 all the way down to times 1. Now that that's sorted out, let's look at this problem. Due to this problem's complexity, there are multiple ways to solve it. We're just going to look at one method today. I would like to divide 300 factorial by 200 factorial. That should leave us with 201 times 202 times 203 all the way up to times 300. On the screen here, I have split these 100 numbers into 50 centralized pairs. When I see this, it reminds me of a formula that says a plus b times a minus b is equal to a squared minus b squared. Well, since these pairs are centralized, meaning they derive from the same number, in this case the number right in between 201 and 300, so 250.5, we know that a stays the same with a value of 250.5 for all pairs. However, b, assuming it is positive, gets larger and larger as the number in pairs move away from each other. As b gets larger, b squared gets larger. So a squared minus b squared gets smaller, meaning the product of each pair gets smaller as the numbers in the pair move away from each other. Therefore, out of all the pairs, according to our logic, 201 times 300 should result in the lowest product. Because we know that 200 times 300 is equal to 60,000, that's easy to calculate. So 201 times 300 should be larger than 60,000, which means that every single pair out of the 50 pairs has a product larger than 60,000. So the 50 pairs multiplied together would have a value much larger than 60,000 to the 50th power. Moving on to the next slide. Okay, so using the same logic, we can easily prove that 200 factorial divided by 100 factorial is larger than 20,000 to the power of 50. 100 factorial divided by 50 factorial is much larger than 5,000 to the power of 25. 50 factorial divided by 20 factorial is larger than 1,000 to the power of 15. 20 factorial divided by 10 factorial is larger than 200 to the power of 5. And 10 factorial is larger than 3 million. You can use a calculator for this. Because all these values are bigger than a number, so we can say that the product is bigger than the value of all the numbers multiplied together. So 300 factorial divided by 200 factorial times 200 factorial divided by 100 factorial times 100 factorial divided by 50 factorial times 50 factorial divided by 20 factorial times 20 factorial divided by 10 factorial times 10 factorial is larger than 60,000 to the power of 50 times 20,000 to the power of 50 times 5,000 to the power of 25 times 1,000 to the power of 15 times 200 to the power of 5 times 3 million. That was a lot of numbers to read. Okay, so anyways, the left side of this, after doing cross multiplication, you would realize is equal to 2 to the power of 80 times 3 to the power of 51 times 5 to the power of 1 times 100 to the power of 280. And it is also equal to 300 factorial. So let's start something new here. We know that 2 to the power of 40 times 3 to the power of 51 is larger than 2 to the power of 40 times 3 to the power of 40, which is equal to 6 to the power of 40, which should be larger than 5 to the power of 40, which is larger than 5 to the power of 39. So summing that up, 2 to the power of 40 times 3 to the power of 51 is larger than 5 to the power of 39. Therefore, 2 to the power of 40 times 3 to the power of 51 times 5 is larger than 5 to the power of 40, which is also equal to 25 to the power of 20. So from that, we get that 2 to the power of 80 times 3 to the power of 51 times 5 should be larger than 25 to the power of 20 times 2 to the power of 40, which is equal to 25 to the power of 20 times 4 to the power of 20, which is 100 to the power of 20. So therefore, 2 to the power of 80 times 3 to the power of 51 times 5 times 100 to the power of 280 is larger than 100 to the power of 300. And because we already know that 300 factorial is larger than this value, so 2 to the power of 80 times 3 to the power of 51 times 5 times 100 to the power of 280, because we know this, and also because we know that 100 to the power of 300 is smaller than that, so therefore 300 factorial is larger than 100 to the power of 300. Again, there are a lot of numbers here, and it's definitely challenging to comprehend. So you can always look at the slides because all the information that I've just spoken out has been listed there. So we have arrived at the conclusion that 300 factorial is larger than 100 to the power of 300, so we are done. Thanks for watching, guys, and hopefully you've learned something from this more challenging video on indices laws and exponents. See you guys next time. Hope you guys enjoyed this video. Please like and subscribe, and yeah, see you next time.